Right, in a previous video, we defined the curl operation, curl of a vector field, and here are some examples that you could try to just practice the computing of the curl. We also learned about the divergence operation, and here are some examples of vector fields that you could try to compute the divergence of. Okay, so one thing that we want to look at particularly in this video is the curl operation. And there's something interesting to note here that if the vector field, for example, is f1 comma f2 comma 0, let's say that you have a vector field that only is essentially happening in a vector field that's essentially only doing something in the xy plane, right? And we make a further assumption that f1 and f2 are functions of only x and y. So there's no z component of this vector field, okay? This is for I going from 1 to 2. If you were to compute the curl of the vector field here, right, then you would get 0 comma 0, and then when you get to the z entry, you'll get f1y minus f2x. Okay, now that's something, a particular combination of derivatives that we've seen before. And so, for example, if you take this curl and you assume that you make an assumption that the curl comes out to be the 0 vector, then one thing that you can conclude here is that f1y minus f2x is equal to 0, which is the same thing as f1y is equal to f2x. And it was this particular combination of derivatives, f1y being equal to f2x, that was essentially our test for whether or not the vector field f is conservative. Okay, so what we have here is a clue about how we could test vector fields that aren't two-dimensional. So here what we did a trick. We took a vector field f, a two-dimensional vector field. F1 is a function of xy, f2 is a function of xy, and we know that f is conservative if f1y is equal to f2x. And then what we did, we tricked this two-dimensional vector field, we tricked it into 3 dimensions so that we could then compute the curl of it. The curl is an operation on 3-dimensional vector fields, and that gives us 0, 0, f1y minus f2x. So what we can say here is that a vector field is conservative if its curl is equal to the 0 vector field. If the curl is equal to 0, then the vector field f is conservative. And this is a nice test because this curl operation extends to the vector field being 3D, and we can determine if a 3-dimensional vector field is conservative or not. Okay, and that will come in handy. That will come in handy when we try to do the fundamental theorem of line integrals. Okay, so one thing that we can say here is that if we have a line integral along some curve of f dotted with dr, okay, so here's our line integral of a vector function, that we know that this is the integral from t is equal to a to t is equal to b, the vector field along the curve dotted with r prime of t dt. That's the way we've written it in the past. But we can also write that line integral in what is called differential form. And here we're making the assumption that our vector field is f1, f2, f3, and each of those entries of the vector field is a function of x, y, and z. Okay. So we know that this line integral can also be written as the integral between along the curve C, and that curve C likely has endpoints P and Q. So let's say that our curves, P and Q, and your curve C is a curve that does whatever it does, but ends at the point P and starts at the point P and ends at the point Q. And then we know that this line integral is the same thing as saying f1 dx plus f2 dy plus f3 dz. These are saying the same thing, okay? These three different integrals, okay? Now, one thing that will be nice is that if we'll know the answer to this problem, the fundamental theorem of line integrals will kick in, and essentially we'll know that if this line integral will evaluate to a potential function at the point Q minus a potential function at the point P if the vector field F is conservative. Okay, and a vector field F is conservative if that vector field is the gradient of some function phi. But how do we know that a vector field is the gradient of some function phi? There's a test for it now. If our vector field is three-dimensional, we simply need to check that the curl of the vector field is equal to 0. If the curl of the vector field is 0, we know that there is going to exist a potential function phi whose gradient is the vector field F. Okay? So there's the test for whether or not the vector field is conservative, and if so, it makes it nice and easy to evaluate that line integral. Just the potential function, you just take, the potential function evaluated at P, the potential function evaluated at Q, and then you compute this potential difference. Okay, so you'll subtract those two numbers. So if you know the curl is 0, then we can find the potential function by just integrating the first entry of the vector field with respect to x, integrate the second entry with respect to y, integrate the third entry of the vector field with respect to z, and then look at all those, and you basically just look for unique terms. Okay, and that would be how you would find your potential function. Okay, so let's look at an example of this. So once we knew our curl operation, we were able to return to the line integral of vector fields and do the fundamental theorem of line integrals. Okay, so let's look at an example of this problem. Here we can see that so this is just an example we had from the textbook. They want you to show that this given vector field is conservative. Okay, and when they say it's natural domain, they just mean that notice that this function, just the domain on which this function actually exists. So this function, this vector field, is defined for all values of x, y, z. So we don't really have any there's no division by zeros or anything like that to happen in this problem. Okay. All right, so the thing I want to do in this problem, you can see here that the book is computing a wide variety of partial derivatives in this case, and essentially they're just computing the curl. Okay, they're computing the first entry of the vector field, here's the second entry of the vector field, here's the third entry of the vector field, and they're computing the curl of this vector field. Okay, so we're going to go ahead and compute that curl now, and we'll check I'll leave you to check these partial derivatives, but essentially we have a vector field F. The first entry of the vector field is e to the x times cosine of y. The second, plus y times z. The second entry of the vector field is x times z minus exp of x times the sine of y. And the third entry of the vector field is x times y plus z. Okay, so there's our vector field. Let's double check to make sure we've typed it correct. Looks good to me. Okay, and now you can compute the curl of this vector field. Okay, curl of the vector field f with respect to x, y, and z. And you can see here that the curl comes out to be the 0 vector field, which means that this vector field is conservative. That means that there is a function phi, that this vector field is the gradient of phi for some phi. Now we need to find that potential function, and the easiest way to do it is just to integrate the first entry of the vector field, integrate that with respect to x. Okay, integrate the second entry of the vector field with respect to y. So we're going to integrate the second entry of the vector field with respect to y, and then integrate the third entry of the vector field with respect to z. Okay, integrate the third entry of the vector field with respect to z. Okay, and we essentially need to look for unique terms. Okay, so when you integrate f1 with respect to x, integrate f2 with respect to y, and integrate f3 with respect to z, we can see the answers that we're getting over here on the left, and we're looking for the unique terms. So we can see an x, y, z, that's common to all of them, so we're going to write it down. Then we have a unique term, e to the x cosine of y, and then we also have z squared over 2. So you only write the unique terms. I mean, don't write the repeats, write the unique term. And so there is your potential function phi. Okay, and we knew that when we did this problem that it was going to be the correct potential function. Okay, so we have the curl being 0 tells us that there exists a potential function, and we can find that potential function by integration and picking the unique term. Okay. Now that we know that a vector field is conservative, we'll be able to use the fundamental theorem of line integrals in the next video.